So we see here the calendar up to the middle of April, and you just finished entering a discussion post about intelligence, and I'll be talking about more about that in the coming few days and weeks. And you have a discussion post for the ethics discussion coming up on Wednesday, and I sent an announcement, and the announcement had to do with what I'm looking for in this particular post. And I'm looking for, and again, I had given you this link. Let me show you this story analyzer dashboard. This is basically the text of your earlier ethics discussion post. And so I have for each one of you, I have basically what you wrote. So I have for Mund what he wrote, and then for Brendan, and etc. All the way down. So it's basically the entire text your of your discussion. And I added a new thing, as I tell you in my announcement. And this I have people, groups, interactions, and then the ethics word cloud. And here are the each of the different 8 key questions. And as you can see, a lot of folks talked a lot about rights and about liberty, a little bit less about authority, and a little bit less of these other things. And what you see, for example, under rights, you can see that what I have in purple are the ethical concepts, and some of the rights have to do with privacy. Most of the rights really have to do with privacy, for example. And you can see liberties, freedoms, etc. So this gives you the ability to kind of focus in on what you had been saying before about this. And I would like you to kind of build on that and continue that. But another thing I want you to do is to start to tell the use case story. And you've taken or are taking systems analysis and design 454, and you're trying to tell stories about use cases with that. I imagine you've even drawn use case diagrams. And so just the description of how this is used and what you get from it and what it gives you, those kinds of things are things I'd like to see as part of this discussion as well. So part of the discussion is continuing with the ethics piece and maybe starting to focus more on these things that we didn't have so much before. You know, there's very little on character. There's some unfairness, a little bit unfairness, but outcomes. I mean, some of these things haven't been fleshed out maybe as much as they could be. And then in addition to that, the use case. So that's what I'm looking for between now and Wednesday. Play with the tool, play with the toy, and discuss a little bit more with ethics and about your playing with the toy. So that's what I'm looking for between now and Wednesday. I have, let me go back here to the home page. I have and now you're going to have your NoSQL exercises coming due. And so today what I would like to do is to talk about this notion of recursion, and we're going to apply it to the ability to navigate through and display the bill of materials. Recursion works very well when you're dealing with hierarchical kinds of things. And so I want to spend a little bit of time talking about recursion, and then in the next video, we'll actually do some coding to implement recursively navigating through a bill of materials and ultimately displaying that in a visualization. So if I go to the modules, and you will notice that in the NoSQL databases module, I have this PowerPoint called Recursion, so I'm going to download that. And I'll open it up. So this has recursion, and there's going to be some Python examples that we can look at. Recursion, unfortunately, is not something that I think we teach much in 331. Uh, I'm not sure the degree to which Dr. Izzo uh, teaches it. I didn't. I used to teach 331, and I didn't really focus on recursion. But I think that recursion is something that's very important to understand if you're going to do stuff related to AI and analytics and things of that nature. Recursion is a very important um, programming technique when you're doing stuff related to AI, and we're going to see examples of that when we discuss AI later on. So what's recursion? Well, in programming terms, recursion means that a method or a function calls itself. Uh, and we'll see some examples of that where we have the function, it has a certain name, and within the function, it's calling that name again. Very powerful, as I said. There are many mathematical functions that are recursive in nature. There's a lot of different algorithms that can be done more efficiently using recursion than not. And in particular, when we're dealing with a tree data structure, which is a hierarchy, recursion comes in very, very handy. And as we'll see, every recursion has two different conditions that it's got to be testing for. One condition is, do I want to call myself? And that's the recurse case. And the other condition is, do I want to stop calling myself? And that's often called the base case. So you have to want to stop calling yourself at some point. Otherwise, you're going to just keep calling yourself over and over and over and over again. If that were going to be the case, and if we didn't have a stopping case, then our program stack would grow and grow and grow and grow because again, the method, every time a function calls itself, the stack grows, the call stack grows, and then eventually you run out of stack space and it would kind of basically blow up. It's kind of like an infinite regression. So we have to prevent that infinite regression. And this notion of infinite regression kind of brings up some of the, maybe what you might even call mystical qualities of, I can't, hold on a second while my PowerPoint is hanging, and then I'll talk about this. Why is this not? I'm going to pause. Okay, so the PowerPoint was hanging, but I think I got it now. So as I was saying, this notion of infinite regression kind of brings up something that you might even call some mystical qualities of, again, there we go, mystical qualities of recursion, in the sense that recursion is self-referential. A function is referring to itself, and there's all kinds of paradoxes that come up in logic and computing, and even in art, as you can see here. Which hand is drawing the other hand? That sort of thing. By the way, this is a drawing by an artist named Escher, and there is a very, very interesting book that gets into a lot of these different kinds of paradoxes called Gödel, Escher, and Bach in Eternal Golden Braid. You probably know who Bach was, this composer, and Gödel was a mathematician in the 1930s who was very instrumental in computing theory. And he came up with this notion that some things just are not computable. And a lot of that has to do with self-referential kinds of things. And so here's an example of a paradox here. This sentence is false. Well, okay, is the sentence true or is it false? Well, if it's true, then, and it says it's false, it's kind of contradicting itself. Am I lying when I say the sentence is false? Well, if I'm lying, but then it becomes true, and so it is false, and so there's a contradiction. So this kind of notion of self-referentialness is a paradox, and it is also something that is very, very instrumental, as I said before, in artificial intelligence kinds of activities, which makes AI kind of a paradox. And even the question of consciousness comes into play with things of this nature. So there's a lot of links that might be of interest to you to just kind of explore this philosophical tangent that we're going on. But let me come back to the practical matter, and we'll talk about a little bit about recursion and we're going to see how we can implement it in Python. And we'll look at a very simple example here, which is factorial. Now, factorial is an example of a recursive function, because basically this is the function. N factorial, the symbol exclamation point means factorial, equals n times n minus 1 factorial. So here's the factorial being applied both in, this is my end result, but also within the function itself. This called the same kind of factorial function. And as I said, every function has a base case and a recurse case. In this case, 0 factorial is 1, or for that matter, we could say 1 factorial is 1 too. We can as well. We can just go down as low as 1. So we're talking about positive numbers here when we're talking about factorials. So let's take a look at this code, and I'm going to go ahead and copy it. And I'm going to paste it into the shell. I got an empty Python shell here. And so here's my function. And if I want to know what 3 factorial is, I'll just say factorial 3, and it's going to tell me it's 6, because 3 times 2 times 1. If I want to know what 4 factorial is, factorial 4, and it's 24. 5 factorial 5, and that's 120. So when we look at the code here, and you can see that in the code we have a base case. So if n equals 1, I'd return n. And we have a recurse case. And that's what we did for that. So how would this manifest itself in an execution of this function? And in particular, what's going to be happening in memory? And you learned already about things like the call stack. I'm sure those of you in 331 have done lots of stuff with the call stack, and we touched upon it also in 221. So let's take a look again what's happening. Every time a function calls itself, a frame gets placed on top of the stack. So let's start with the main frame, which is basically the shell. Here we are about to call factorial. And the value we're going to pass is a 3. So we've got this literal 3 that's going to wind up being passed. We call factorial, and here a frame for factorial gets placed in. Well, what is that frame going to contain? It's going to contain the local value. So there's a local variable, I should say parameter called n. And now we're doing this test here, and it's not 1, it's 3, so we're about to make another call. We make another call, and another invocation of factorial is placed, and it has its own internal n, which is a different n from this n. And that had what the original 3 minus 1 was, which is a 2. And again, the base case test fails, and we recurse again. And we finally get to the point now where it's been called a third time. So from the main called factorial, which called factorial, which called factorial, and now at this point, the base case or the stopping case succeeds. We're going to return a 1, and the frame's going to pop from the stack. That 1 then winds up getting multiplied by this 2. So 2 times the 1 here, which then gets multiplied by this 3. So it would be 3 times the 2, and then the result is going to be 6. And so there you have it. So this was a very simple use of recursion, and basically all that happened was that the function is calling itself once each time, and then frame stack is growing, and then it's shrinking. Very simple thing. As a matter of fact, this particular example, it would be trivial to do the same thing in a loop. In fact, let me do that. I'm going to do the same thing with a loop. I didn't really need recursion for this. It's a recursive mathematical function, but I could have implemented it in a loop. Let me do that. I'm going to use a variable. I'll call it n, and n will be the number that I want to get for factorial. So let me just do n equal 3. And I'll start my factorial at 1. So I'll have f for my factorial number, and then I'll basically keep changing it in a loop. I'm going to say for I in range, and my range should start at 1, and then it should go to n plus 1. And here's my loop. And I'm going to say f times equal f times equal I. And so that loop has executed. What is f? And f is 6. So 3 times 2 times 1, or 1 times 2 times 3. I could do the same thing. I'll say n equal 4, and refresh f equal 1 again, and then I'll just copy this loop again, and you'll see that we'll come up with the 24. And so what's f is 24. So as you can see, it's a trivial case, really, and simple to do in a loop. But a reason that it's simple to do it in a loop is that we're only calling ourselves once. So let's look at a different situation where we call ourselves twice. And that situation, a classic mathematical function for that is called the Fibonacci number. The Fibonacci occurs throughout nature. It's a really fascinating phenomenon. It produces this kind of a spiral effect right here. The Milky Way galaxy kind of follows that. Here's a snail that kind of follows that. Check out this video. It's pretty cool. And by the way, I also encourage you to check out these links as well. Interesting stuff. So that's the value of that. And notice that what is the Fibonacci number doing? Well, here's our base cases, well, this would be an error case, but here's our base case right here, which is if it's 1 or if it's 2. So if the number is a 1, the Fibonacci number of 1 is 0. The Fibonacci of 2 is 1. And then in general, the Fibonacci number of n is going to be the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. So in this case, we're calling Fibonacci twice. So it's not just like the stack is growing and then it's shrinking. What's really going to wind up happening is the stack is going to grow a little, shrink a little, grow a little, shrink a little, grow a little, shrink a little. And in the process of that taking place, we're going to be basically traversing a tree, a hierarchy. In fact, we're going to be doing a depth first traversal of the tree. Let me just copy this code. So here's the function. And paste it into here. I'm going to kill the shell and bring up another shell. Now I'm going to paste it. And so if I wanted to know the Fibonacci number of 1, oops, I didn't spell it right. Fibonacci number of 1, it's 0. Fibonacci number of 2 is 1. And now let's see as we go up. Number of 3, Fibonacci number of 4, Fibonacci number of 5, and so on, 6, etc. Number of 7, number of 8, and now you can see it's going to start growing by a little bit more each time. So that's the kind of thing that you get with the Fibonacci number. Now, as I said, it's calling itself twice. This is going to be harder to do in a loop. It can be done in a loop, but it's going to be harder to do, and it'll be much easier to do it recursively. And essentially what's happening, as I said, is this depth first traversal in this hierarchy, this tree. So at the very first time, if we have Fibonacci of 4, what is that? The Fibonacci of 3 plus 2. So the first thing that's going to happen is that we're going to call Fibonacci of 3. So we're adding something to the stack now. Now the stack is 2 levels deep, and we're traversing down here. Well, what's Fibonacci number of 3? Well, that's the 2 and the 1. And so in order to evaluate the Fibonacci number of 3, we have to evaluate the Fibonacci number of 2. So that starts us traversing down this tree again. Now the stack has grown to 3 levels deep. And then we go down 1 more level to 4 levels deep. The stack is 4 levels deep at this point. So, but at this point now, we're done, we return, the stack pops, we're again down to 3 levels deep. But we were in this expression here where we had to call Fibonacci again, we're down to 4 levels deep again. Then down to 3 levels deep, and at this point this gets returned down to 2 levels deep, but we have to make the call here, brings it back up to 3 levels deep, 2 levels, 1 level, and so you can kind of see the pattern of what's happening. And that pattern is, in fact, a hierarchy. It is a tree. In this case, it's a tree where out of each node of the tree, we have we're branching, we have 2 branches coming out of each node of the tree. You might call this a binary tree. In fact, that's a term that's often used for this. So this is a tree where we have a branching factor of 2. And how deep are we going? Well, it depends on what the value is that's entered. If we had done Fibonacci of 5, we'd be going deeper. Fibonacci of 6, we'd be going deeper. But point being, we're traversing a tree, a hierarchy. Now, let's look at another example. Tower of Hanoi. It's actually a game. And it was one of the very early kind of simple toy little AI problems. You'll probably see it in AI textbooks. And here's the nature of the game. You have 3 pegs. You have some number of discs that will be stacked on the pegs. The goal is to get them all to the second peg. They were originally stacked on the first peg. Always a smaller disc is going to be on top of a bigger one. You can't put a bigger one on top of a smaller, and you can only move 1 disc at a time. And so here is the code for that. And again, in this code, you will see 2 calls to the function. Let me pull up another idle here. Oops, that's not what I wanted. Oh, there we go. Okay. So paste this in. That's our function. And before I run it, let me kind of step through what it's going to be doing. You'll notice that there's 2 calls, and anytime there's a call, you're going to be doing something. You're going to print something, and this is the stop condition, by the way, if n equals 1. You're going to print something, and then you're going to call once, print something in between that first call and call. So point being, if we stop, we're just going to print this out, but otherwise we're going to make a call, do a print, and make a call. And this will kind of give you, and I'm going to, I ran it, and you can see what it gave me as a result here. And let's take a look at what's happening in the code here. So we first start out with the values that were passed was 3. Tower of Hanoi, you got 3 discs. Here's our 3 discs. We started with the disc on peg A. And so how are we going to move these discs? Well, we can only move 1 at a time. So essentially we're going to move 1 to 1 place, and then another to another place, and then another to on top, and then that kind of thing is how you're going to be playing this game. So let's watch it happen. So here's our stack at 1 level deep, 2 level deep, and you can see a disk is moving, Another disk is moving. Notice that it's growing a little, and then it's shrinking, and then it's growing, and then it's shrinking. So it's very kind of mysterious how it's doing this. Recursion is sometimes kind of hard to follow exactly what's happening, but it gets the job done. And so that was the end of that. So in both of these cases, the Tower of Hanoi and uh, in the Fibonacci, we were essentially constructing a binary tree because we were doing exactly, let's go back to this code, we were calling within the function, it calls itself twice. The same thing was true here. Within the function, it calls itself twice. So this is the kind of navigation that was taking place. The branching factor of the tree, in other words, the number of branches was always 2. However, you can have in principle any number of branches, and you can go as deep as you need to go. And so I have an example here. I'll give the last example here, which is I call it recurse demo, and I'm going to go ahead and copy this code of the function and pull up a shell. Go ahead and yeah, pull up the shell again. And I'll go ahead and paste in function definition. And let's say I want to have 4 branches and go 2 deep. So I'm going to say recurse demo, and I'm going to start at depth 1, and I want to go 2 deep, and let's see what I'm going to have here. Oh, sorry, number of branches is 4, so I'm going to want to have 4 branches. I'm going to start at depth 1, and I'm going to go 2 deep, and oops, oh, I forgot something. Sorry. I have to have a variable that I'm calling node number. And that variable is going to be a global variable, and it's going to, I'm going to increment it each time. So we'll number each node that gets printed out at the time it gets printed out, in the order that it gets printed out. So I'm going to make node number equal 1, and now I'll call recurse demo again. And you can see we only went 2 deep. Here's the first level, here's the second level, and this is the order in which they were done. Let me modify that a little bit. I'm going to set node number to 1 again, and let me modify that a little bit. And I'll again make it 4 branches for each node, but this time I'll go 3 levels deep. And you can see at each level you have 1, 2, 3, 4 nodes. At the next level you have 4 nodes, so 4 branches. And this is the order in which they're done. Again, a depth first traversal. I want to make that clear. What's happening here is something called a depth first traversal. Let me go back up. Not, for example, that we're starting here at this first node up here, and then going across, and then going across, and then going across. That's actually called a breadth first traversal, and there is an algorithm for doing that. What we're doing is a depth first traversal. And it's possible to do this without recursion, but guess what you're going to need? If you wanted to do this, you're going to need a stack, because you're going to have to keep track of where you are. And the beauty of recursion is that we can just let the call stack take care of that. And so let me continue with that. So anyways, that's our little foray into recursion. And we're going to use this for the bill of materials, because the bill of materials, well, a particular component can have any number of subcomponents, right? So we don't know what our branching factor is going to be. It could be different in different cases. And it could go as deep, obviously a bicycle's bill of material is going to go a lot deeper than a gear shift's bill of materials, because a gear shift is part of the bike. And so we're going to work with Recursion for bill of materials, and then as a result of that work, not only are we going to be able to kind of print things out and make them look come out sort of like we're seeing here with this, but also we'll be able to get into displaying a graphical image of a tree. And at that point, you're going to learn a little bit about D3 and scalable vector graphics as well, at least a tiny little bit about it from this exercise that we'll do the next time. So until then.